Hi, my name is Adson and my co-author is Professor Carl from Universidade Federal of ABC. Our title is a numerical nonlinear dynamics study of simplified two-phase flow model for pipeline riser system. We consider multi-phase flow in pipeline riser system present in offshore oil production facilities like this in the picture. This talk outline is introduction, methodology with 1. Model two-phase flow control volume approach. 2. System dynamic studies, stationary states, their stability and the basing of the attraction, Poincaré maps, periodic orbits, and the possibility of the chaos, and Lyapunov experiments to check the possibility of the chaos. Results and references. The motivation. Multiphase flow in pipeline riser system with the section with downward inclination angle followed by a section with upward inclination like a riser under low liquid and the gas mass flow rates are flown to hydrodynamic instability. An example such the instability in several slugging. The movie illustrates the hydrodynamic instability. Notice that the gas passage from the pipeline to the riser is blocked during this intermittent flow behavior. The pipeline and the riser are modeled as control volume. We consider two configurations. The first configuration is when there is gas passage from the pipeline to the riser, and the second configuration, the gas passage is blocked at the riser base and the partial pipeline flooding may occur. Variable X measures the pipeline flooding. The variable are made dimensionless. The governing equation for configuration if gas passage from the pipeline to the riser are 1. The riser control volume liquid mass conservation equation. 2. Equation result form the combination of the riser control volume and the liquid mass conservation equation. 3. The pipeline control volume liquid mass conservation equation. 4. Algebraic equation result form the gas riser pipeline control volume conservation equation. 5. The riser control volume linear momentum equation. 6 and 7. Rift flux closed law in terms of the riser bottom and the top variables. 8. Algebraic relation for the pipeline void fraction. 9. The riser control volume liquid mass. 10. No pipeline partial flooding. 11 and 12. Additional relations are used to keep the number of the equation the same in the both configuration. The governing equation for the configuration without gas passage from the pipeline to the riser and the partial flooding are almost the same. To the governing equation for the first configuration, 1 to 9 equations are dissimilar. 10 is the pipeline stratified flow control volume liquid mass conservation combined with the liquid front kinematic relations. 11 and 12 equations follow from the fact that there is only liquid at the riser base. Model governing equation in matrix form. We have a system of the differential equation. Z is the transposed vector representing the dependent variables and the non-zero elements of the mass matrix. The first configuration as the given below by equation, and the mass matrix is non-zero elements for second configuration. Linear stability First, we obtain the stationary state. Only the first configuration has a stationary state, and it's denoted as Z asterisk the solution of 8 of the Z equals 0. To study the linear stability of this stationary state, we obtain the stationary state perturbation governance equation, where matrix 8 of the Z asterisk is the Jacobian of the vector 8 of the Z evaluated at the Z equal Z asterisk. If the perturbation grows with the time, the stationary state is unstable, but if the perturbation decays with the time, the stationary state is stable. The methodology to study the nonlinear dynamics of the present model is composed of the following steps. 1. Use a Lyapunov function to estimate the stationary state basing of the attraction. 2. Build the Poincare maps to study the existence of the periodic orbit and see if chaotic behavior is possible. 3. If possible, the chaotic behavior shown in the Poincare maps, use Lyapunov exponents as a second criterion for chaotic behavior. This numerical exercise is left as a future work. We show stability map for the pipeline riser system used in Verkadin experiment. The system parameters value and the given in the table. At the horizontal axis, there is the gas superficial velocity at the pipeline entrance, and at the vertical axis, there is the liquid superficial velocity at the pipeline entrance. For each pairs of the superficial velocity, we evaluate the stationary state and study its linear stability. The symbol marked in red in the figure means that stationary state for respective pair of the superficial velocity is unstable, and the symbol marked in the blue means that the stationary state is stable. In this figure, we illustrate the vector field behavior in the vicinity of the stationary state for each pair at the superficial velocity. Pink means the stationary state is a saddle. Blue means the stationary state is a stable focal node. Green means the stationary state is an unstable focal node. Black means the stationary state is a stable node. The transition from stable focus node to unstable focus node is associated with a Hopf bifurcation, as we illustrate in next slide. We fixed the liquid superficial velocity to 0.1 and vary the gas superficial velocity along the yellow line arrow, illustrated in the figure. In the table next to the figure, different values of the gas superficial velocity are displayed with the eigenvalues associated with the linearized system of the equation. We see that as we cross the transition from the stable focus node to the unstable focus node, two eigenvalues become pure imaginary numbers, typical behavior of the Hopf bifurcation. Therefore, in the region with the green color, we showed expected the existence of limit cycles. Our references used so far in this work in progress. Thank you for your attention. My email is